Hello students, welcome to this session of Chemical Kinetics. In this session we'll be discussing about the integrated rate equation for the first order reaction. That is for the reactions which obey first order kinetics. So we'll be deriving the equation or that integrated rate equation for the first order reactions, and we'll be also discussing about the half-life of the first order reaction and the units of the rate constant, and we'll take up the examples. We'll be also solving few numericals related to the first order or this order of the reactions, that is where the integrated rate equations are applied. Right? So let's start our theory session here. Now what is a first order reaction? In a first order reaction, what happens? That the rate of reaction is proportional to the molar concentration of the reactant raised to the power 1. That is, the actual coefficient is 1. Right? So let's take up this example. This is A is converted to B. Now the reaction rate, it can be given as minus of dA by dt. What is this dA by dt? It is the change, I hope you know this. So change in concentration of A. A is what? That is a reactant at any instant of time. Or this also gives you the instantaneous rate. Now that is equal to Ka. What is this K? K is the rate constant, and A to the power the actual coefficient, that is 1. Right? Now what this equation signifies, that if the concentration of A is doubled, the rate will be also doubled. That is, the rate of reaction depends on the concentration of single entity, or there is one variable in the rate law expression. Now what we can do, we can just integrate this. Integrate the concentration within the limits, that is A0 to A. A0 is the A0 is the concentration at time is equal to T0, and A is the concentration at time is equal to T. So the time can be integrated. These are small times, that this is dt is what? At any instant of time. And this minus of dA by A can be also, or is also integrated. So after integrating this, we'll get the integrated rate law equation or rate equation for the first order reaction. Let's do this. Now see here, the integration of dA by A. The limits are A0 to A. A0 is the concentration of A when time is 0. That is when the reaction has just started. And A is the concentration when time is T. That is, the reaction maybe it is completed or it is halfway. Right? And it is integrated between them. Or this is the final concentration, we can say. And K, and this is integrated within the time limits T0 to T. The T is the any time. Now the integration of this particular value is log natural A plus K into KT plus I. So integration dt is equal to T. Now in this case, we have to find out the value of this integration constant. So when time is 0, what will be the value of the concentration? It will be equal to A0. So from here we can get I, the value of I, that is the integration constant, and that is equal to log natural A naught. Right? Now put this value in the place of I, and we'll get the equation over here. That is K is equal to 1 by T log natural A naught by A. Now just convert into log base to the 10. So it will be, this is log base 10. So K is equal to 2.303 by T A naught by A. Right? This is the exponential form of the equation. Now what this equation shows? This equation shows that the concentration of A decreases exponentially with time. So how the concentration of A is decreasing? A is what? The reactant. The concentration of reactant is decreasing exponentially with time. So this is the equation for the first order, for the reactions which obey first order kinetics. There is a relationship between the rate constant, the time, and the initial and the final concentrations. Now let's calculate the time required for the half-life, or the equation for the time required for the half-life, or the half-life you can say. It's not the time required. Let's find out the equation for the half-life of the first order reaction. See, if I'm taking A, what was the equation? The K is equal to 2.303 by T log of A naught, that is the initial concentration, divided by the final concentration. Now let's take up A as the initial concentration. So what will be the final concentration? It would be A minus X. Right? So A is the amount of the substance initially. Now what we are talking about? We are talking about is the half-life. That is time required before the reaction to complete by 50%. Right? Or when the concentration of the reactant has reduced to its 50%. So here, if I'm just putting the time as T half, the A that is the initial concentration, will be reduced to its half. So it will be A by A minus A by 2. Just solve this, we'll be getting log 2. That is T half is equal to 2.303 by K log 2. Now what is the value of this log 2? It is 0.693. So time required for the completion of the reaction by 50% is how much? 0.693 by K. That is, half-life period of first order reaction is independent of the concentration of reactants. Right? So we can say that time required for the completion of any fraction of the reaction. Say if it's here A by 2, I can put it A by 4 also. So the time required for the completion of any fraction of the reaction is independent of the concentration of reactants. Whereas if I take up the zero order reaction, in the case of zero order reaction, what is the thing? T half is equal to A naught by 2 into K. That is, the half-life or the time required for any fraction or for the completion of any fraction of reaction is dependent on the initial concentration. So there is a difference between the half-life period for the first order and this zero order reaction. Now in this case, T half is equal to 0.693 by K. Now what will be the unit of K here? Now in this case, K, that is the rate constant, is independent of the initial concentration. So what will be its unit? It will be time inverse. That's it. And it can be anything. It can be the minute inverse or second inverse. Right? So this is half-life period of the first order reaction. Now this is the equation for the first order reaction. That is the relationship between the final concentration, initial concentration, the rate constant and the time. Right? What we got was K is equal to 2.303 by T log of initial concentration divided by the final concentration. Now this equation can be written in the form of y is equal to mx plus c. That is the equation for the straight line. So we have just written it in the form of equation for the straight line. That is, on the y-axis what is kept is log AT, that is the concentration of the reactant at any time t. T is the time, and log A naught. A naught is what? It is the intercept, or C. A naught is the initial concentration of the reactant, and this can be calculated from this intercept. So then what will be the slope of the line? It will be minus of K by 2.303 R. So the integrated rate equation for the first order reaction can be written in the form of the straight line equation, that is y is equal to mx plus c, and the graph which is plotted between different values or between the values of log AT and time comes out to be a straight line with a slope equal to minus of K by 2.303 R. It is minus of K by 2.303. It's not R. It is 2.303 by, minus of K by 2.303. R is not here in the equation. right? So this is the slope of the graph. Now students, this is a very simple thing. Finally, that is deriving the equation for the first order kinetics, or for the first order reaction, for the second order, for the zero order. Difficulty comes when you have to apply these concepts for solving the numericals. See, if you're given a graph like this, and I'm saying that the value of slope is somewhere between, it is k, no? So the value, its unit will be time inverse. So the value of slope is something 20 second inverse, right? It means you have got the rate constant. I'm giving you that the slope, the value of the slope is this. Find out the half-life of the reaction. Now here, as we know the value of the slope, and slope is what? Slope is minus of k by 2.303. Now from here we can find out the value of k. Now once you have got the value of k, we can easily find out the half-life of the reaction. So we'll be doing the numericals also related to this. Let's first find out the, we have already find out the unit for the rate constant of a first order reaction. And what is it? It is second inverse. Or that is the time inverse. It may be minute, it can be second, or it can be hour. Now let's take up its examples. Then we'll switch to the numericals. Here are a few examples. Hydrolysis of sugar to glucose and fructose. That is sugar C12H22O11 plus of H2O. It is giving what? It is giving C6H12O6 plus of C6H12O6. That is the glucose and fructose. This is a first order reaction. How come? There are two reactants. Now the question arises, when there are two reactants, how can this have the first order kinetics? How can the rate of reaction be proportional to the concentration of C12H22O11 only? So this is the case when the other reactant is taken in large excess. So in this case, the concentration or the water is taken in large excess, and when the reaction proceeds, there is very small change in the concentration of water. Now that is not affecting the rate of reaction. So these are called as pseudo first order reactions also. Now the second example is the nuclear disintegration reactions. See, the disintegration of plutonium or thorium or uranium. These all obey the first order kinetics. Next is the growth of bacteria. That is the rate of growth of bacterial culture until the nutrients are exhausted follows the first order kinetics. That is, the rate of growth of bacteria is proportional to the how many cells are there? The cells of bacteria. Right? Until the nutrients are exhausted. That is, once the nutrients are exhausted, obviously bacteria can't grow. So if we start with 2 cells of bacteria, it undergoes binary division. Right? So the rate of the reactions depends on the number of cells of bacteria. Right? So the growth of bacteria follows the first order kinetics. Even the population growth. The rate of growth of population obeys first order kinetics if there is no change in birth and death rates. So these are very important ones, students. These all obey the first order kinetics. Right? And the rate constant or the half-life can be calculated by using the equations of the first order kinetics. Right? Now let's solve few numericals related to the first order kinetics and also the zero order kinetics, because see, numericals are very important. After all, you have to apply these concepts for finding out the half-life or the reactant concentration nor the rate concentration. That is very important. So let's solve few numericals. Now let's take up this numerical. That is a reaction that is of first order with respect to the reactant A has rate constant of 6 per minute. If we start with A, that is with 5 mole per liter, when would A reach the value of 0.0405 moles per liter? So it's like we have been provided with the value of K with the initial concentration and the final concentration. And what is asked? What is asked is the time. So can we easily calculate the time? Just write the equation for the integrated rate equation for the first order reaction, right? So what is the integrated rate equation for the first order reaction? It's K is equal to 2.303 by T log of the initial concentration divided by the final concentration. Now what all we are having? The initial concentration is given as 5 mole per liter. The final concentration is 0.05 moles per liter. We are provided with the value of K. Let's put the values in the equation. So we'll get 6 is equal to 2.303 by, what is the time? Time we don't know. Now log of the initial concentration, that is the 5 divided by 0.05. Just solve this. Now what will be this log of 5 by 0.05? It will be log 100, right? Or T is equal to 2.303 by 6 log 100. It's 6, it's not T. So here log 100 is 2. Now your T will be equal to 2.303 into 2 divided by 6. So just find out the answer. What will be the thing? It will be 2 into 2 is 4. Just take it approximately, and this will be something 0.76 minutes. So this was a very simple question. You have to just put the values in the equation, right? In the equation for the first order reaction. Now let's take up our second question. The question here is the reaction sulfuryl chloride, that is SO2Cl2, dissociating giving SO2 and Cl2, that is sulfur dioxide and chlorine. Sulfuryl chloride dissociates giving sulfur dioxide and chlorine, is a first order with K 2.2 into 10 to the power minus 5 per second. What percentage of SO2Cl2 would be decomposed on heating at 320 degrees centigrade for 90 minutes? Now what all other things given is, we are provided with the time. Time is given in minutes. Now time is given as 90 minutes, whereas the value of K is given in seconds, that is equal to 2.2 into 10 to the power minus 5 seconds. Now while solving the numericals, do keep one thing in mind: all the units should be similar. It's not that K is in seconds and time is in minutes. So what will be the time here? Time here 90 into 60. Now it is asked what percentage of SO2Cl2 would be decomposed. It means we have to take initially, that is the initial concentration of A as 100. Let's start with A as 100, right? Now what is the equation for the first order reaction? It is K is equal to 2.303 by T log of A naught, that is the initial concentration, divided by the final concentration. Now the K value here is 2.2 into 10 to the power minus 5. That is equal to 2.303 by T. What is the time? It is 90 into 60 minutes, 60 seconds. Now log of 100 divided by 100 minus X. Let X has been dissociated, right? So this 100 by 100 minus x will be equal to what? This side, this is log, so this side it would be anti-log. Anti-log of 90 into 60, right, multiplied by 2.2 into 10 to the power minus 5 divided by 2.303. So solve this complete thing and take out its anti-log. So just solve it. 100 by 100 minus x anti-log. After solving it, you'll be getting 5158 into 10 to the power minus 5. So just take out the anti-log of it. So what will be the answer? It would be 100 by 100 minus 6 is equal to 1.126. Right? So it's 100 by 100 minus x is equal to 126. Find out the value of x. X will be equal to 100 minus 100 by 1.126, and your x will come out to be 11.2%. Right? I think you can solve this expression. Now x is 11.2%, that is how much has been dissociated in 90 minutes. What is the percentage dissociation in 90 minutes? It's 11.2%. So in this question also what you have to do is, you have to just put the value in the formula. That's it. Let's take up our next question. It's a different type of question. Say find the 2/3 life of a first order reaction in which K is 5.48 into 10 to the power minus 4 per second. Again, it's a first order reaction. What will be the equation? Integrated rate equation. It is K is equal to 2.303 by T log of the initial concentration divided by the final concentration. Right? Now what is it saying? It is 2/3 life you have to find out. It means, say, let's suppose A0 is equal to small a and A is equal to A minus x. Now what is x equal to? X is equal to 2 by 3. 2/3. That is, the dissociation is 2/3. Right? So the K value here is 5.48 into 10 to the power minus 4, that is equal to 2.303 by T log of A by A minus 2 by 3A. X is what? X is 2 by 3A, and T is what? T 2 by 3. Fine. Now let's solve this. A by A minus 2 by 3A. What will be the answer of this? It will be A by 3, or this will be equal to 3. Let's put the value. Let's put 3 over there. So it would be 5.48 into 10 to the power minus 4 is equal to 2.303 by T 2 by 3 log 3. So what is log 3? It is 0.477. Right? At least you should remember the values of log 2, 3, 4 and 5. So log 3 is equal to 0.477. Now we can find out T2 by 3. Just calculate it. So you'll be getting T2 by 3 as 3, that is 2005 seconds. So the time required for the reaction to be completed 2/3, or the time required for the 2/3 completion of the reaction is 2005 seconds. Right? So what will be the answer? It is 2005 seconds. We can convert it into minutes, just divide it by 30. So it will be approximately 33 minutes. right? That is time required for the completion of the reaction by any fraction depends on the initial concentration. Remember this thing in the case of first order reaction. So this is the way we'll solve this question. Now let's take up our next question. This is our question. A first order reaction is 75% complete in 60 minutes. Find the half-life of this reaction. So the question can be solved in two ways. First of all, we can I'll use that elaborate one, that is K is equal to 2.303 by T log of A by A minus X. Now what is X? X is 75% complete, right? So that is 75 by 100 into A. So that will be equal to how much? 3 by 4A. Now we can put this value over here. So K is equal to, this will be what? A minus X. This complete thing solved. What will be the answer of this? A by A minus 3 by 4A, or it would be A by 4, or it would be 4. So let's put the value 2.303 by T. T is given as 60 minutes. Log of 4. Now what you have to find is the value of log 4, right? So just solve this question. You'll get your K as 0.0232 minutes inverse. Now what is asked? You're asked to find out the half-life of this reaction. Now what is half-life equal to? T half is equal to 0.693 by K. So T half will be equal to 0.693 by 0.232, right? Now just solve this. 0.0232. When we'll solve this, we'll get the answer as 30 minutes. So this is the elaborate one. That is, you have to take out the equation, or you have to write the equation for the first order rate kinetics and put in the value, find out the value for K, and then find out the half-life. Despite this, we can do one simple thing. See, a reaction is 75% complete, means it has completed 2 half-lives, right? So 2 half-lives is equal to how much? 60 minutes. So what will be 1 half-life? It will be 30 minutes. We can find out like this also. So 75% complete is 2 half-lives, right? First half-life is 50%, second is 75%. So we can find out the answer by this also. It will take just few seconds, that's it. Just like you just read the first order reaction is 75% complete in 60 minutes. Find the half-life of this reaction. 2 half-lives is 60 minutes, so 1 half-life would be 30 minutes. Now in your board exams, when you're expected to do the solve the numerical step by step, use this elaborate process, whereas when you're giving the competitive exam, just use this method, right? Now let's take up our next question. Our question is, a first order reaction is 20% complete in 5 minutes. Calculate the time taken for the reaction to be 60% complete. Now in this case you can't do anything. You have to take that elaborate one only. Now just write what all are the things we are provided with. It is the time, that is equal to how much? It's 5 minutes. And it is for the completion of 20% of the reaction. That is, what is the value of X over here? X is what? X is equal to 20 by 100 into A, or it is 0.2 A. Now let's find out first the value of K. Because for finding out the time required for 60% completion, we should know the value of K, because we've got only one equation, that is K is equal to 2.303 by T log of initial concentration divided by the final concentration. See students, you can use this equation for solving the questions of this radioactive disintegrations also. Now we have to find out the value of K. K is equal to 2.303 by T. What is the time? It's 5 minutes. Log of the initial concentration, it's percentage, so we have to take it 100, and that divided by, I can take it as 1 also here, right? So if I'm taking it as 1, so 1 by 1 minus 0.2 A, that is A by 1 minus 0.2 A. It is A minus, not 1 minus. So your K will be equal to 2.303 by 5 and log of 1 by 0.8. So just solve this, you'll get your value of K, and that comes out to be 0.044 per minute. Now when you have got the value of K, we can easily find out the time for 60% completion. Again, put this value of K in the first order equation, and what you'll get is, see, 0.044 is equal to 2.303 by T log of A by, now it's 60%, so it will be A minus 0.6, right? Or it would be 1 by 0.4. So 0.4044 is equal to 2.303 by T log of 1 by 0.4. Just solve this and you'll get the time as 20.5 minutes. So in such cases where the two conditions are given, say first of all the time taken for 20% completion is asked, and the time taken for 60% completion is asked, and you are not provided with the value of K also, then you first need to calculate or find out the value of K, and this is the way you can find out the value of K, right? So it is 20%, so it's 0.2A. Fine. Now let's move to our next question. It's a very good question. Show that in case of a first order reaction, the time required for 99.9% of the completion of the reaction to take place is 10 times the time required for half-life of the reaction. That is, it is saying that T 99.9% completion, or we can say T 99.9% completion is equal to 10 into T half, right? So what you have to calculate first is the time for the 99% completion. Okay, now we can't calculate the time because we don't have this rate constant with us. Now let's start with the equation of the first order reaction. That is, K is equal to 2.303 by T 99.9 into log of, it would be A, it is 99.9%, so A minus 0.99A will be the thing, right? Or K is equal to, you can solve this equation, 2.303 by T 99.9 and log of, it would be what? It would be 1 minus 0.999, or it can be written as log of 10 to the power 3. Just solve this, you'll get 10 to the power 3. Fine. So K will be equal to 2.303 by T 99.9 and log of 10 to the power 3. So log of 10 to the power 3 is what? 3. So it would be 3. Now K will be equal to 6.909 by T 99.9 and K is equal to 0.693 by T half. This is the equation. Now what is K? K is a constant. So can we equate the two things? K is constant for the reaction. So 0.693 by T half will be equal to 6.909 by T 99.9. Now can you derive this expression that T 99.9 is equal to 10 times the T half? Yes, of course we can. It is, see, T 99.9 divided by T half is equal to 6.909 divided by 0.693. From here you'll get what? That T 99.9 is equal to 10 times the T half. Got it? So this is the way we can find out the time required for the completion. See students, it can be 75% or it can be 50% also. Fine. I can say that time required for 75% of the reaction to take place is 2 times that required for T half. That we can also prove like this. Fine. And remember, these are just tricky questions. These are the easy ones, I suppose. You can do them easily. Now let's take our next question. Our question is, a first order reaction has K is equal to 1.5 into 10 to the power minus 6 at 200 degrees centigrades. If the reaction is allowed to run for 10 hours, what percentage of initial concentration would have changed in the product? What is the half-life of this reaction? Now we are provided with 10 hours, right? That is the time. Time is equal to 10 hours and it is 1.5 into 10 to the power minus 6 second inverse. So it has to be changed into seconds. So 10 into 60 into 60. So this will give you 3600 seconds. 000 seconds. Now let's take initial concentration as 1 mole per liter. Now let's put the value in the equation for the first order reaction. So K is equal to 2.303 by time, that is 10 into 60 into 60. Then log of A is 1 by 1 minus X. We don't know this 1 minus X. So this 1 by 1 minus X will be equal to the antilog of what? What is the K value here? 1.5 into 10 to the power minus 6 into 10 into 60 into 60, and that divided by what? 2.303. Right? So it's 1.5 into 10 to the power minus 6. It's not minus 9. So just solve this. So you'll be getting 1 by 1 minus X as 1.055. From here you can easily get your X, and X comes out to be 0.052. Solve this equation. I think you can easily solve the multiplications, the divisions, find out the antilog, and then find out the value of X. My part is to tell you the solution, the procedure, the formula. So yeah, you can easily do this. Your X is 0.052. Now, how much percentage has been changed into product? So it will be approximately 5.2%. So 5.2% has changed to product in how many hours? 10 hours. Now what do you have to find out? You have to find out the T half-life. Right? That is the time required, T half-life or the half-life. So T half is equal to K by, or 0.693 by K. So T half will be equal to 0.693 by K is given 1.5 into 10 to the power minus 6. Just solve it and you'll be getting your half-life as 128.33 hour. Right, your time is given in seconds. So you'll be first getting the answer in seconds, that is 462,000 seconds, and convert it into hours. Because there for the reaction 10 hours had been given. See, the time for the reaction has been given as 10 hours. So you have to find out the half-life of this reaction in hours only. Right? So these are the types or patterns of the questions which come from this topic. So this is the questions related to the first order reaction. I hope you have understood this section, students. This application of the concepts is very, very important, I tell you. Now there is one more formula, that is the amount of the reactant left after n half-lives. It is the amount of the reactant left after n half-lives. Now let the initial concentration of reactant be A. So the amount of reactant left after n half-lives is equal to A by 2 to the power n. You can use this formula also to solve the questions. Right? So these are the types of questions which are there from this topic. There are many more types of questions. We'll be discussing them later. These are just related to the first order kinetics. Now I'll be concluding this session, students, and in the next session we'll be discussing about the equations or the rate equations for the second and the third order reaction. We'll not go into the details of it, and we'll be proceeding towards the Arrhenius equation also, the effect of temperature on the rate of reactions. Thank you, students. Thank you for listening patiently, and do have a nice time ahead.